Hello all. Uh, Today I'm gonna try to fly over this paper because Greek Easter is in 2 days. So I have things to do, so I will try to go over it fast without compromising the quality of what we demonstrate here, okay? So this is unit 1. You can see it over there from the most recent examination period of January 2026, okay? And there is also a unit 1A version of this paper, which is different. Hopefully I'm gonna solve that one and upload it soon, okay? Let's dive in. Section A, multiple choice questions awarding 1 mark. As I said a billion times in past videos, this question should take you about a minute. So you should devote about a minute per mark. So if a question awards 10 marks, it should take you 10 minutes. And other general things, of course, is that if you don't know how to answer a question, just skip it and come back later. Go over the questions you know how to solve first, and so on and so forth. Okay, question 1. Which of the following units can be used for a vector quantity? From a quick inspection, you can see that newtons can only be used for vector quantities, okay? Because joules, kilograms, and watts are scalar quantities. Describe scalar quantities. Okay. Question 2. An apple falls freely from rest until it reaches the ground. The apple falls a distance s in a time t. Which of the following gives the relationship between s and t? And from the Suvat equations, we know that s is the initial speed times t plus 1/2 at squared. In this case, the initial speed is 0. I don't know why this pops up all the time. In the bottom, I mean. So initial speed is 0, the acceleration is g, so 1/2 gt squared. Therefore, s is proportional to t squared. I mean, I'm talking about this thing. Downloading writing aids for what language is that? I mean, if you guys know, let me know. Okay, so the answer is D. Okay, question 3. A white ball moving with velocity v collides with a stationary red ball of the same mass. After the collision, the white ball is stationary and the red ball moves with velocity v. Which of the table describes what happens to the total kinetic energy and total momentum of the balls during the collision? Okay, so since all the velocity is transferred from the white ball to the red ball pretty much, and both have the same mass, this means that momentum is always conserved, okay? So from this column, the only answers that make sense are B and D, because momentum is always conserved, okay? And in this special case, kinetic energy is also conserved because we have the transfer of velocity from one ball to the other. Therefore, the correct answer is D. Okay, and you can draw a scheme if you want. So you have the white ball, and let's say that this is the red ball. So this is again. Now it pops up with a different language. I don't know what's wrong with this. I keep saying hide, but it pops up. So we have the ball moving to the right with velocity v, and this one is stationary, and this is the situation before. And then after, we have the white ball being stationary, and the red ball moves to the right with velocity v. The masses are the same, and so easily, you can see easily that we have conservation of kinetic energy. Okay, question 4. A toy car rolled down a ramp. The ramp was at an angle theta to the horizontal. The resultant force on the car was F. The car moved a horizontal distance x and a vertical distance y as shown. Okay, which of the following gives the work done by F as the car moved down the ramp? Okay, so basically, they give us the resultant force. The resultant force includes gravity, friction, whatever else is there. So we don't care about the type of the force at all, since it is given to us. And we know that work is force times displacement in the direction of the motion, right? So force times, let's just write D. Okay, so we basically need to find the length of the hypotenuse of that triangle, And we can use, you cannot use Pythagoras and say, that's the square root of x squared plus y squared, because it's not, none of the options give you that result. Therefore, we have to use the fact that cosine theta, I'm going to call this L. So cosine theta is x over L. Therefore, L is x over cosine theta. Therefore, the work done is going to be F times the displacement, which is L in this case. So that's F times x over cosine of theta, which is option B. Okay, I hope this makes sense. Moving on, a force of 20 newtons and a force of 35 newtons act at a point. The forces act at right angles to each other as shown. Which of the following expressions gives the magnitude of the resultant of these forces in newtons? So this is a case in which you can use Pythagoras. Okay, so the resultant will be this one. Okay, and it's going to have a magnitude of square root of 20 squared plus 35 squared. Okay, so that's option D. But let me tell you something that you can use, a trick in these types of questions. So let's examine option C. Option C has the forces squared. So this is a quantity that has units of newtons squared. So this cannot be the magnitude of a force. Similarly, option B has the quantity force under a square root. So this will have units of square root of newtons. So that cannot be the answer. So the only possible answers that make sense dimensionality wise, okay, are A and B. Okay, so that's another way you can figure out these questions. Okay, moving on to question 6. A driver applies the brakes to stop a car. The car has a constant deceleration. Which of the following shows the velocity time graph for the car as the brakes are applied? Okay, so using Suvat equations, the velocity is given by u plus at. Okay, so in this case, the acceleration is negative because it's a deceleration. So we will have v is equal to u minus at, which is a straight line with a negative gradient, just like b. Okay, you can see it there. So pretty much, if this is time and this is v, then for time equal to 0, if we plug in time equal to 0, we have that v is u, so this y-intercept is u pretty much, okay? So this was question 6. Moving on to question 7. A person doing a parachute jump falls at terminal velocity. The person is connected to the parachute by cords as shown, okay? Which of the following is the Newton's third law pair to the force of the cords on the parachute? Okay, so the cords constitute the first body, and the parachute is the second body. Okay, so option A says the air resistance on the parachute. That cannot be it because air resistance is a different type of force. Okay, so that's totally wrong. Option B, the force of the cords on the person. No, because we are examining, so in this scenario, we have three bodies. The first body is the parachute, the second is the cords, and the third is the person. So option B has to do with the person, so it's irrelevant to us. Then option C, the force of the parachute on the cords, which is exactly what we need. So that's the correct answer. And then D, the weight of the person. That's a different type of force. So you see again how 2 out of the four options are totally wrong, and these are D and A because they describe different types of forces. And then B describes a plausible Newton's third law pair, but we are not caring about the person, we care about the parachute and the cords. Okay, so option C is the correct one. Let's move on. Okay, question 8. A student applied a tensile force to a metal wire of length x and cross-sectional area A. The extension of the wire was delta X. The student applied the same force to a second wire made of the same material. The extension of the wire was delta X over 2. Which row of the table could show the length and cross-sectional area of the second wire? Okay, I worked this out the long way, I would say. So if you can think of an easier way, please let me know in the comments. But this is what I did. So let's say that this is the first piece of wire, okay? And let's assume it has a length X and a cross-sectional area A, and a tensile force F is applied to it, and it extends by delta X. Delta X, not delta X over 2, excuse me. Now the second piece of wire, here it is. We apply the same force X on the second wire, but now the length is X prime, the cross-sectional area is A prime, and it extends by delta X over 2. Okay, let's use everything we know. So the extension is given by delta X over X, and stress is extension times the Young's modulus, right? Okay, now stress is force per cross-sectional area. Extension is delta X over X. So we take the extension from here and plug it in there, times the Young's modulus. Therefore, delta X is X over A times the force over the Young's modulus. Okay, in the second case, and I'm going to use a clean page, for the second wire, delta X prime is going to be X prime over A prime, the new length and cross-sectional area, times force over the Young's modulus, because these two quantities are the same. We apply the same force, we have the same material. The same material has the same Young's modulus. Okay, but delta X prime is delta X over 2, right? And this is equal to X prime over A prime times the force over the Young's modulus. But now delta X is known from here, right? So we can plug in to the left-hand side. So we have, let me think, what am I trying to do? So X over A times force over the Young's modulus is equal, I'm taking the 2 to the other side, 2 times X prime over A prime times force over the Young's modulus, and this cancels. So we see that X prime over A prime is 1/2 X over A, pretty much. Okay, so if you go back to the table, basically what this equation says is that the length is the same and the cross-sectional area is twice that of the initial wire. So that's option B. Okay, so I took the long path to finding this answer, but I hope this makes sense. Okay, question 9. The force extension graph for a spring is shown. A tensile force of 50 newtons is applied to the spring. An additional tensile force of 300 newtons is then applied to the spring. Which expression gives the change in elastic strain energy in joules when the additional force is applied? So it gave me a lot of trouble, and I was eventually not able to find which option of the 4 was the correct answer. So this is what I did instead. And okay, in the end, I did find the answer, but I couldn't see it from the way these answers are structured. So delta E elastic would be 1/2 times 350 newtons, okay, because it says an additional tensile force of 300 newtons in addition to the initial 50 newton force, okay, so 350 newtons is the force. And this extends, if we go to the plot, we see that at 350, so this is the extension at 350, okay? So the extension is 7 pretty much. So 7 times 10 to the negative 3. And then we have to subtract the initial energy, which is 1/2 50 times for 50 newtons. the extension is this one, okay? So that's the 50 newtons and the extension is 1. So I'm using the graph for this case. 1 times 10 to the negative 3, okay? And if we do the, if you carry out this calculation, you will find 1.2 joules. Okay, so I found 1.2 joules, and then I evaluated all these 4 expressions, and I found that option C evaluates to 1.2 joules. So I chose that option, and by checking the mark scheme, that was actually the correct answer. But if there is a faster way to do this, guys, please let me know in the comments. I don't know. I wasn't able to see in this case that option C was the correct option. So it gave me some trouble, I would say. Okay. Now option 10. By the way, these questions were hard, I think. I mean, this test was a hard test, I believe. So anyway, a student hangs a 3 kilograms mass and a 2 kilogram mass from a spring as shown. The forces on the 3 kilograms mass are in equilibrium. The string holding the 2 kilograms mass breaks. Which expression gives the initial upward acceleration of the 3 kilograms mass in terms of g? Okay, so in the initial scenario, before the string breaks, so initially we have the forces, the weight of the two masses, so 5g is equal to k times the extension of the spring. So the extension, I don't know why I put prime, sorry. So the extension x is 5g over k, okay? Now, when the string is cut, okay, so in the final scenario, okay, the forces on the 3 kilogram mass are only due to the spring and the mass. So what I'm trying to say is that imagine, okay, let me draw it over here. It's gonna be easier. Okay. So the scenario is like this. Okay, so that's the 3 kilogram mass. So there will be a force of 3g, 3 kilograms times g, and times g is the weight, and the force kx pulling it upwards. And which x? This x, the one we just calculated, okay? And it's gonna move upwards, so the acceleration is gonna be up. So we have to use kx minus 3g equals to ma, and the mass is 3 again. So what I'm trying to say is that the equation of motion is going to be kx, because it points in the same direction as the acceleration, so it's positive, minus the weight, 3g, is equal to ma, and the mass is 3a, right? So the mass is 3 and then a. Okay, now x, we can plug in from what we just calculated. So k times 5g over k minus 3g is equal to 3a. So k cancels, and we find that the acceleration is simply 2 times g over 3. So that's option A. Okay, section B, question 11. A car accelerates from rest on a horizontal road. The engine causes a forward force on the car of 7,500 newtons. Okay, the weight of the car is 15,000 newtons. Okay, the road exerts a normal force N on the car. Complete the free body force diagram for the car at the instant the acceleration begins. Okay, so we will assume that one box, so this box, or better yet, we will assume that this represents 5,000 newtons. Okay, so this way, since the weight of the car is 15,000 newtons, we will need 3 boxes. So 1, 2, 3. Okay. So that's going to be the weight. So the weight, let's do a red, let's use red color. Okay. So this is the weight, which is 15,000 newtons. And you see that we do need to use scale pretty much. Okay. And then since the car is not moving up and down, I mean, it's not going to fly, it's not going to take off, hopefully, okay, then the normal force is going to point up, okay, and it's going to be equal to the weight. Okay, so that's the normal force, also 15,000 newtons. And then the driving force from the engine, let's use green, is going to be 7,500 newtons. So it's going to be 1.5 boxes. So here, so that's going to be the force from the engine. Okay, so that's the force, which is 7,500 newtons. Okay, and this is a complete answer, I believe. Okay, and we used scale, we drew all the forces, so we are ready to go. Okay, I mean the car is ready to go, not us. Okay, let's move on to the next question. A crane lifts a load of 3,400 newtons through a distance of 26 meters. The power input to the crane is 5.7 kilowatts. The efficiency is 0.38. Calculate the time taken for the crane to lift the load. Okay, so first of all, let's find how much energy we need for the lift. Okay, so we need to lift a load of 3,400 newtons through a distance of 26 meters. So the energy from the lift, okay, is going to be 3,400 times 26. Basically, this is F times delta S, right? Which is the work done, pretty much. And yeah, I'm gonna erase this. And if we evaluate this, we find 88,400 joules. We are multiplying newtons times meters, which is joules, right? Okay, let's move on. Now, the useful energy, okay, P useful. Okay, so that's how much energy we will need. Now, the crane provides 5.7 kilowatts, an efficiency of 0.38 though. Okay, so the useful power is 2,166 watts. Okay, now P useful is going to be energy over time. So time is energy, and this is the energy we need from the lift, for the lift, excuse me, over power. Okay, so 88,400 joules over 2,166 watts, which is joules per second, right? So we'll need 40.8 seconds, which is about 41 seconds. Okay, this was question 12. So once I think the important thing to realize here is that you have to multiply with the efficiency coefficient to find how much useful power this crane provides. Okay, moving on. Okay, question 13. In a game called curling, I don't know why they write it like that. I mean, it's a kind of well known. Players slide circular stones across ice towards a target. In one game, stone A moves towards the target and stone B is stationary. Stone A is about to collide with stone B as shown. Okay. Question A. During the collision, there is a resultant force on stone A and a resultant force on stone B in the opposite direction. These forces have the same magnitude and act for the same time. Explain how Newton's second law predicts that momentum is conserved when stone A collides with stone B. Okay, so first of all, the stones experience the the stones experience equal forces, right, in opposite directions. Okay, and at the same time. Okay, So basically, F times delta T is the same. Okay, so they have equal and opposite changes in momentum. So equal and opposite changes in momentum. Okay, so the momentum lost by stone A equals the momentum gained by stone B. Okay, so momentum is conserved. So I'm sorry to do this to you, but I want to go back to the first sentence. So the stones, experience equal forces in opposite directions that last for the same time. Okay, so that's the important thing. So uh, that last for the same time interval is the correct expression. Okay, that last for the same time interval. So F times delta T is the same. Okay, I think it's a better formulation of the sentence. Okay, excuse me about that. I mean, forgive me. I mean, sometimes, what we wrote before is not totally wrong, but I think this clarifies what's going on. Okay, so let's move on to part B. Before the collision, stone A had a kinetic energy of 3.8 joules. Stone B was stationary. After the collision, stone B moved, excuse me, with a speed of 0.45 meters per second. Stone A will slide past the target if the momentum of stone A after the collision is greater than 5.5 kilograms times meters per second. Deduce whether stone A will slide past the target. Okay, so um, let's let's draw the situation. Okay, let's create a clean page. So we have before and after. Okay, so we have stone A with velocity VA, UA, okay, and stone B, which is stationary. Okay, and after the collision, we have both stones moving, so VA and VB. All right, so this is the situation. So we need to find the initial speed. So we have they give us the initial kinetic energy of stone A, so we can use that. So 1/2 ma times ua squared is 3.8 joules. Therefore, ua is the square root of 2 times 3.8 over 18, and this is equal to 0.65 meters per second. And now we can use conservation of energy, of momentum, excuse me. So the initial, ma times the initial velocity ua plus 0, I mean, the b is stationary, is equal to ma times va plus mb times vb. I mean, you can take it from the scheme there. I mean, va and vb. Okay, so let's solve for va. So va is going to be MAUA minus MBUB over MA. And this is equal to 18 times 0.65 minus 17. I'm sorry. So 17 times 0.45 over 18. So this is 0.22 meters per second. And now we can find the momentum after. So the momentum of ball of stone A. So PA prime is MAVA, and they give us the mass of stone A as 18 kilograms. So we have 18 times 0.22 is equal to 4.05 kilograms meters times seconds minus 1, which is less than 5.5 kilograms meters per second. So it won't slide past. What was the statement? Deduce whether stone A will slide past the target. So it won't slide past the target. Okay, as I said, I found this paper a little bit difficult, to be honest. Okay, this was question 13. Let's move on to question 14. Okay, question 14. A container is used to hold plants. The container hangs by a chain from a bracket attached to a wall as shown. Okay, not to scale. Okay. The bracket has a horizontal bar with a hook at one end. There is a supporting bar beneath the horizontal bar. The container is in equilibrium. State why the center of gravity of the container is vertically below the chain. Okay, so this because that's an axis of symmetry and there is no resultant moment. So axis of symmetry and also no resultant moment. All right. Part B. A screw in the wall exerts a force F on the horizontal bar as shown. That's the force F. Okay. The weight of the container is 34 newtons. The mass of the bracket is negligible. Determine force F. You should take moments about point P over there. Okay. So first of all, we will need to find this length over here. So let's call this X. Okay, so we need to find this length X. So we can take the moment, we need to take the moment F times X about P. So we need to find X first. So the tangent of 55 degrees is pretty much 0.16, right? Because this is a right triangle. So 0.16 over X. So X is 0.16 over the tangent of 55 degrees. So that's 0.11 meters. Okay, so F times 0.11 meters is going to be equal to the weight. So that's the weight over here. So the weight is exerting a moment of 34 newtons times this distance from P. So times 0.28. So the force is equal to 84.97 newtons, which is approximately 85 newtons. And this was question 14. Moving on, question 15. A can of spray paint contains a paint and a solvent, which are both liquids. The can also contains a ball bearing. When the can is moved, the ball bearing moves through the paint. Stokes' law applies as the ball bearing moves through the paint. State the conditions for Stokes' law to apply. So we need a laminar flow, right? Small spherical object and low speeds. Okay. Part B. Stokes' law applies as the ball bearing moves through the paint at a constant velocity. The ball bearing moves a distance of 5.6 centimeters in a time of 1.3 seconds. Okay, that's important. Calculate the viscous drag due to the paint acting on the ball bearing, and they give you the radius and the viscosity of paint. So first of all, let's calculate the velocity. velocity is distance over time. So 5.6 times 10 to the negative 2 over 1.3. This yields 0.043 meters per second. And then the force is just 6 pi times the viscosity, sorry, of the paint, eta, times the radius, times the velocity we just calculated. So 6 pi times 0.15 times 0.9 times 10 to the negative 3, which is the radius, times 0.043, and this yields 1.1 times 10 to the negative 4 newtons. I was being a little bit lazy with the units, so let's demonstrate the units. So we have eta, which is pascals times seconds, multiplied with the radius, which is in meters, and then multiplied with velocity, which is meters per second. And you can see easily that seconds cancel, and we have pascals, which is newtons over meters squared, multiplied with meters squared. So this indeed yields units of force. Okay, let's move on. Part C, when the can is shaken, the ball bearing moves. This causes the paint and the solvent to form a mixture. The viscosity of the mixture is different from the viscosity of the paint. The ball bearing falls through the mixture at terminal velocity. Calculate the viscous drag due to the mixture on the ball bearing, and they give you the mass of the ball bearing, then the density of the mixture, and okay, the radius of the ball bearing, which was given before. Okay. All right, so basically now the scenario is a little bit different. So let's say that we have the ball. I'm going to draw it over here. Okay, what kind of forces are exerted on it? The weight, right, down. The drag, let's use a different color. Oops, I said different color. Okay, so that's the drag, D, and then we also have the upthrust. Okay, all right, so the upthrust and the drag force should be approximately equal. So let's make this vector for the weight a little bit longer. Okay, so this force is balanced to have terminal velocity. Okay, so in general, we would have that the weight, because the ball moves down, we take the positive direction to be down. Okay, so the weight minus drag minus the upthrust will be ma, but the acceleration is 0 when we reach terminal velocity. So basically we have the drag is equal to the weight minus the upthrust. Okay, what's the weight? The mass of the ball times g. And what's the upthrust? It's the density of the mixture times g times the displaced volume, which is the volume of the sphere, right? So we have m times g. The mass is 2.4 times 10 to the negative 15 times 9.91, 81, minus the density, which is 1.5 times 10 to the third times 9.81 times 4/3 pi, and then the radius to the cube, 0.9 times 10 to the negative 3 to the cube. Okay, and if we evaluate these expressions, we find 1.91 times 10 to the negative 4 newtons, which is the answer. All right, let's move on to question 16. The photograph shows a tennis racket. I used to play tennis when I was a teenager. I loved it, but I struggled finding partners to play. I learned how to play on my own, so I was clumsy. I had a really good backhand, but a horrible forehand, which doesn't make any sense. I mean, nobody trained me. If you guys play tennis, let me know. So anyway, okay, we have the string and the racket. A student determined the Young modulus of the material of the string from a tennis racket. She used the apparatus shown below. Okay, we have the clamp, the marker, the distance x, the string. Okay, bench pulley and a mass. The student determined the cross-sectional area of the string. She measured the original length x of the string between the clamp and the marker. She increased the tension in the string and measured the new length of the string between the clamp and the marker. She used her results to calculate the Young modulus of the string. State why the student should suspend a small mass from the string before measuring x. So the string is taut, right? So the string needs to be taut, okay? Because how else are we going to work with it? Okay. B, explain how the student could decrease the percentage uncertainty in the value of x. First of all, the percentage uncertainty in x is equal to the absolute uncertainty in x over x. Okay, so the absolute uncertainty in x is half, is half the smallest deviation of the ruler. So it doesn't change easily. Okay. But if the marker is placed further away from the clamp, then x increases. Okay, so if x increases, the percentage uncertainty in x decreases. So that's one way to decrease the percentage uncertainty. Okay, part C. The table shows the Young modulus of different materials used to make string for tennis rackets. I've never heard of the material called gut. If you guys know what that is, let me know in the comments. All right, the string used by the student had a cross-sectional area of 1.2 times 10 to the negative 6 square meters. The initial length of the string was 1.6 meters. When the student increased the force on the string by 15 newtons, the length of the string increased by 4.2 millimeters. Deduce which material the string was made from. Okay, we're going to use the same ideas as we used in section A. That was a similar question. So extension is delta x over L. Stress is, strain is delta x over L. And then stress is strain times the Young's modulus. So, so basically that's equal to delta x over L times the Young's modulus, and therefore force over cross-sectional area is delta x times E over L. So the Young's modulus is force times L over A times delta x. So that's 15 times 1.6 over 1.2 times 10 to the negative 6. By the way, the units are newtons and then meters squared. And then delta x is 4.2 times 10 to the negative 3, again meters. So we find 4.76 times 10 to the 9 newtons over meter squared, that's pascals. So that's about 4.8 gigapascals. And from the table, we see that the closest is nylon, okay? So nylon is the material. All right, this was question 16. Moving on. Question 17. In a factory, boxes move along tracks. One track forms an inclined plane at an angle of 22 degrees to the horizontal. A box of mass 5 kilograms is placed on the track as shown. Okay. The box slides down the track from rest. Friction acting on the box is negligible. Calculate the velocity of the box when it has moved 2.5 meters along the track. Okay, so 2.5 meters in this direction pretty much. Okay. All right. So sine, first of all, we need to find the vertical displacement. Okay. So we need to find this y. Okay. Sine of 22 degrees is y over 2.5. So the vertical displacement is 2.5 times sine of 22 degrees, which is 0.94 meters. To find the velocity of the box when it moves 0.94 meters in the vertical direction, we use conservation of energy. So basically mg times y, which is the gravitational potential energy when it's up there, is equal to the kinetic energy if we take gp to be 0 at the ground level. Then at the ground level we will only have kinetic energy, so 1/2 mv squared. So v is the square root of 2gy, so that's equal to 9.81 times 0.94, and this is 4.3 meters per second. All right. Part B, it's a long writing problem. The box is placed on a different track in the factory. The sketch graph shows how the displacement of the box varies with time, so displacement and time. Explain what the graph shows about the velocity and acceleration of the box. Okay, so we're going to split our answer into 3 parts. So from 0 to 10, the gradient, which equals the velocity, is constant, okay, which means that the acceleration is 0. And how do we know that? The velocity is constant, doesn't change, so the acceleration is 0. Okay, then from 10 to 20 seconds, we see that the gradient decreases, right? So the velocity decreases, right? So we have deceleration. How do we know that the velocity decreases? Because if you take the gradient, you can see that that's the gradient, and then that's the gradient up there. So you see how the velocity decreases. And in fact, at 20 seconds, the velocity is 0 because the gradient is 0. And then beyond, so excuse me, I said 3 parts, so it's actually 4 parts. Okay, so beyond 20 seconds, the v increases, but in the opposite direction, as you can see, but in the opposite direction. And we know that because the gradient is negative. So in this part of the graph, you see how the velocity starts increasing. All right, this was question which was it 17, okay? And let's move on. In 2009, a satellite orbiting the moon fired a projectile towards the surface of the moon. The initial velocity of the projectile was 2,460 meters per second at an angle theta to the horizontal. The horizontal distance traveled by the projectile was 2,930 meters as shown. Okay, the time taken for the projectile to reach the surface of the moon was 7.5 seconds. Show that theta was about 81 degrees. Okay, so this is a bit complicated. Let me see. So I'm gonna break the motion into two. Okay, into two parts: the x direction and the y direction. Okay, so in the x direction, okay, we have the acceleration in the x direction is 0. The initial velocity in the x direction is u, which is given as 2460 meters per second. So it's going to be u cosine theta, okay, because you have to analyze the velocity into u cosine theta and u sine theta. For those of you who have been watching my videos, when I analyze vectors, the rule I use to remember which one is the cosine and which one is the sine is that when the component touches the angle theta, like in this case over here, That component is the cosine theta. And the other component that doesn't touch physically the angle theta, that's the sine. Okay, so that's what I use. Okay, so for the x component of the velocity, we have 2,460 times cosine of theta. Okay, and in the x direction, we have s in the x direction is ux times t plus 1/2 ax t squared. Ax is 0, therefore we are left with this equation. So we know that it travels for 2,930 meters, and this is equal to 2,460 times cosine theta times the time taken, which is 7.5. So cosine theta is 0.16. So theta is 80.86 degrees, which is about 81 degrees. Okay, so almost vertically, pretty much. All right. Part 2 of this question. Calculate the speed of the projectile as it reached the surface of the moon. Assume the acceleration due to gravity is constant and has a value of 1.63 meters per second squared. So in the y direction, now we have ay, the acceleration in the y direction is 1.63 meters per second squared. So it's easier this way, analyzing the motion in the two axes, so you don't get confused. And use subscripts, it helps. So uy is u sine theta, and now we know sine theta, so that's 2,460 times the cosine of 80.86. Did I say cosine? It should be sine, excuse me. Okay, so this is 2,428.8 meters per second. So Vy, using Suvat equations, is Uy plus A times T. So Vy is 2,428.8 plus 1.63 plus 7.5. So Vy is 2,441 meters per second. Yeah, that's the speed in the y direction. And if you want to find the magnitude of the speed in total, you can use Pythagoras. So v is the square root of vx squared plus vy squared. So that's, let me use a clean page because it's getting confusing. So that's the square root of 2,441 squared plus 2,460 times cosine of 80.86 degrees, and that's squared. So that's 2,472.1 meters per second. Okay, so that's the speed. Now, okay, now part B. A satellite orbiting the Earth could fire a projectile towards the surface of the Earth with the same initial height and velocity as the projectile fired towards the Moon. A student used the equations of motion to predict the motion of this projectile, explaining how the predicted horizontal distance traveled by this projectile will be different from the horizontal distance traveled by the projectile fired towards the Moon. Assume the acceleration due to gravity is constant and has a value of 9.81 meters per second squared. You do not need to do any calculations. So the distance horizontally, okay, will be less than that of the Moon, okay, simply because it's going to move faster, okay, because it's going to take less time. Oops. Okay. All right. So it will fall faster. Okay. The horizontal component of u, though, will be the same. The horizontal component of U will be the same. Okay, but it's gonna fall faster due to the larger acceleration due to gravity. Okay, so it's gonna cover less distance. All right. Part 2, the student used the equations of motion to calculate the speed of the projectile at the surface of the Earth. The student used the value of 9.81 meters per second squared for the acceleration of the projectile. Give 2 reasons why the student's value for the speed would not be accurate. So we will have air drag. So it plays a significant role. So it has to be counted for in the calculation. So air drag will cause horizontal deceleration. Okay. And G is not totally uniform. That's the other thing. It's not totally uniform at 9.1 meters, 9.81 meters per second squared, okay? Because you're gonna throw this from a height. What was the height again? Let's find it. Do they mention this? They don't, but okay, G is not totally uniform in general, okay? It changes with height. All right, this was a long problem. This was question 18. So we are ready to move to question 19. Okay, question 19. A toaster is a device used to heat a slice of bread, okay? A platform in the toaster is supported by 4 springs. A slice of bread is placed in the toaster and a person pushes the platform downwards, stretching the springs. A hook then holds the platform in place as shown. Okay, so that's the hook. So you push it down. All right. Now, part A, explain how the elastic strain energy stored by the springs compares with the work done by the person to push the platform downwards. So first of all, the springs already store some elastic energy due to the weight of the toast. And you can see it over here in this second figure. Okay, so while the platform is pushed down, okay, both the person, both the person and gravity and the gravity is from the bread, okay, from bread, help to stretch, excuse me, to stretch the springs. Okay, so the total elastic strain energy is greater than the work done by the person alone. I hope this makes sense. And this is because the weight of the bread kind of helps us to push the springs down anyway. So the work we do is less than the total elastic strain energy needed to push the strings down. Okay? The springs, down. All right. Part B. The platform is supported by 1 spring at each corner. The 4 springs are identical. A person places a slice of bread of weight 0.52 newtons in the toaster. the weight of the bread causes the platform to move 2.1 centimeters downwards. Show that the stiffness of each spring is about 6 newtons per meter. Okay, so the work done is the force times delta x. So what did I write? K times delta x. And in this case for the 4 springs. Okay, so the weight is equal to the total spring constant times delta x. So K total is 0.52 newtons over 2.1 times 10 to the negative 2. So the total spring constant is 24.76 newtons per meter, and this for the 4 springs. So K for one spring is K total over 4, right? So if we divide, we find 6.19 newtons per meter, which is very close to 6 newtons per meter as required. As the problem states. Right, part 2. The hook exerts a downwards force of 1.2 newtons on the platform. The toaster hits the slide of bread and then releases the hook. The springs return to their unstretched length and the bread is launched upwards. The mass of the platform is negligible. Determine the speed of the bread at the instant the springs return to their unstretched length. Okay, so, okay, let me think. Now, the force we exert plus the weight of the bread is equal to 4K for the 4 springs times the new extension. So the new extension delta x prime, when we push it down totally, is going to be 0.52, which is the weight of the bread, plus 1.2, which is the force we exert, over 4 times 6.2, which is K for each spring, which we take from here. And we round it to 6.2. All right, so this yields 0.069 meters. Okay, now the elastic strain energy is then E elastic is going to be 1/2 times the force plus the weight times delta x prime. So that's 1/2 0.52 plus 1.2 times 0.069, and this is equal to 0.0596 joules. Okay, the gravitational energy is equal to mgh, mg times delta x prime, pretty much, right? So 0.52 times 0.069, so that's 0.0359 joules, and I'm going to use a clean page because it became a mess here. So over here, okay. So what I'm trying to say, actually, let's demonstrate. So when you have the bread down here inside the toaster, okay, so you will have the springs totally stretched. Okay, so basically you take the gravitational GP is equal to 0 up there. So, okay, so what I'm trying to say is that we have to subtract the gravitational potential energy of the bread from the elastic strain energy to find the total energy available to become speed for the bread. I hope this makes sense. Okay, so pretty much delta E is 1/2 mv squared. So delta E is the elastic strain energy, so 0.0596 minus the gravitational potential energy, because the bread is going to travel all the way up here, right? So minus 0.0359, and this is going to be equal 1/2 And I'm going to write m as weight over g times v squared, because they don't give us the mass, okay? They give us the weight, okay? So v is going to be the square root of 2.9.81 times 0.024 over 0.52, which is 0.95 meters per second. Okay, again, to make sense of the energy, we need to first find by how much the force springs will stretch when we apply a force of 1.2 newtons plus the weight of the bread. Okay, so we found the stretching. Now, due to that stretching, we can find how much energy is stored in the springs by using 1/2 the force used, which is the force plus the weight, times that extension. So we find the total elastic strain energy. But then we have to subtract the gravitational potential energy when since the bread is going to travel from down here up there, okay? And that's going to be the available energy to be converted into kinetic energy, okay? That's all. All right, so this was question 19, which is, as you can see, it was the last problem in this very difficult test, I think, okay? But let me know what you think in the comments. Yeah, this was Unit 1 from January 2026, so a few months ago. I hope these videos are useful. Um, the channel is not getting the traction I would like, so at some point I will start introducing other types of videos as well. I'm still thinking about what kind of videos. It's probably gonna be about video games I like to make and physics material like research, physics research, nuclear physics, stuff like that. But I will continue having these videos because you guys find them useful. But I want the channel to become more famous, if that makes sense. Maybe I'm vain, I don't know. But anyway, thank you guys for those of you who are subscribed. Please like these videos. It helps them pop up into search options and stuff like that. And as I said, in 2 days is the Greek Easter. So see you guys. I don't know if I'm going to upload a new video tomorrow. We will see. Bye for now.